Okay, where are we? That was 40. Okay, now on to the interesting one, 41. So that's a circle of radius 2, but interestingly, that's like this. But in fact, you could rearrange it. You see, it's yeah. This one here, y equals root 1 plus x squared, plus and minus though. I think it's like this, is it? Better graph it. That's that. And then okay, yeah. So which area do they want though? I guess this piece? Yeah. Is it this piece they want? And this piece, which will be twice. So I can just focus on this. But they also might want the white pieces. But since it's a circle, I could find both and see which one the answer is at the back. But let's start with getting this one here. So this one here is y equals root 1 plus x squared, that piece there. And then this piece here, that can be from the circle equation, y equals root 4 minus x squared. So we'll call this area A. Area A be the integration. Oh, I'll have to find this point. Okay. So when does 1 plus x squared equal 4 minus x squared? So when does 2x squared equal 3? So that's when x is equal to the root of 3 over 2. Just a plus answer here. Okay, let's just call that alpha. So it'd be the integration from 0 to alpha root 1 plus x squared the x, and then plus alpha to 2 root 4 minus x squared the x. Now, this one we've seen. The trick here is draw a triangle and call this x and this 2, and this would be root 4 minus x squared. And this we can call like u, and you can say like cos u is root 4 minus x squared over 2. And then you can say sine u is x over 2. And you could say cos u equals a half dx du. So this one here, you could change that into 2 cos u, and then the dx is another 2 cos u du. So that would be 4 integration of cos squared u du. But cos squared u, there's a formula for working that out actually, because we have cos 2a equals cos squared minus sine squared, but sine squared is 1 minus cos squared. So you have cos 2a equals 2 cos squared minus 1. So cos squared is cos 2a plus 1 over 2. So that will divide out a 2 there when you replace the cos squared with cos 2u plus 1 du. So that becomes 2 sine 2u over 2 plus u. And that becomes, no, don't multiply just yet, because sine 2u is 2 sine u cos u. So that's sine u cos u plus u. So that's 2. And then sine u is x over 2. And cos u is root 4 minus x squared over 2 plus u. And u is sine inverse x over 2. So that would be, if I multiply in the 2, that would be a half x root 4 minus x squared plus 2 sine inverse x over 2 with the limits of root 3 over 2, 2. Well, that's the right side. But what substitution can we use for the left one? Could we do something similar? Or we have a triangle, and that's 1, and that's x, and that's root 1 plus x squared, and that's v. So v sine v equals x, and then cotan v is root 1 plus x squared. No, sorry, not cotan, sorry. Sine v is x. No, tan v is x over 1. Okay, so that's good. Then what about the root 1 plus x squared over 1? That's like sec. Sec v is root 1 plus x squared. Then the derivative here, so you can have dx dv equals sec squared v. So this integration becomes equals integration sec v times dx, which is sec squared v dv. So that's equal the integration of sec cubed v dv. That is kind of similar to cos cube that we have earlier. So actually, I think it might be better to keep it like sec and sec squared v, but then we have to change the sec squared maybe. We have a formula that cos squared plus sine squared equals 1. But we divide by cos squared, we get 1 plus tan squared equals sec squared. So I could change sec squared into 1 plus tan squared. Does that really help me? Really? Maybe this isn't the best substitution. Let me think for a moment. Yeah, that's quite that's a whole nother question itself. I wonder if there's some other way. That's the area underneath, so that's this area here. We know this area. We know the whole lot. It's a quarter of a circle. So maybe it would be better, because that's actually quite the difficult question. It might be better to think of this area as a quarter circle. So that's a quarter pi r squared. And the r is 2, squared is 4. So that's actually pi. Oh, but we don't know. We don't know this red piece, do we? We don't know this red piece. But by symmetry, this point here is 1, and that's 2. Ooh, by symmetry, is that piece the same as that? So, see. This square I know. Whole thing. Sure. I draw a line here. No, I don't think that's the same. Oh, do I really have to integrate secant cubed? Any clever way to avoid it? You said this is integration of sec v sec squared v dv. Don't think I have any choice. Oh, I'm gonna have to use a substitution here. W equals sec v tan v. So dw dv would be derivative of sec times tan. I forgot what's the derivative of sec. Sec is 1 over cos. cos to the -1. So bring down the power, reduce the power by 1, and then multiply by sine. So that's sine over cos squared. So that's sine and secant squared, huh? Or if you want to have tan in it, it's tan sec. That might be better. Yeah, tan sec. So that's tan v sec v tan v. So that's tan squared. Plus sec cubed, because it's sec by sec squared. Sec cubed v. So the integration of sec cubed v would be w with the limits. Sec v tan v with the limits. Minus the integration of tan squared v sec v dv. Now we need another. I think we should change tan squared into sec squared minus 1. Sec v tan v minus the integration of sec squared v minus 1 sec v dv. It's actually pretty good because that becomes sec v tan v minus the integration of sec cubed v plus the integration of sec v. So something interesting happens here, which I can kind of show you. So if you have a situation like you're trying to integrate something, like let's say integrate whatever f is, and then as you're using your substitutions, yeah, and you arrive at some expression minus the integration of f again, you can take that over to the other side. You get twice the integration of f equals that expression. So then the integration of f just becomes that expression over 2. So basically what I can do is I can drop this and I can say it's a half sec v tan v plus the integration of sec, which, oh, that's probably going to be somewhere here. I'll pause it while I find what it is. I think it's in the book. So the formula for integrating sec, and I'll have to prove it on the next page, is log sec v plus tan v. Now I have to go back to what v was. So that's a half, and sec v is root 1 plus x squared. Tan v is x, and log sec v is root 1 plus x squared, and tan v is x. Okay, so if I multiply in the half, similarly, that's a half times x times root 1 plus x squared plus a half times the log, and then I'll put in the limits, and this one is 0 to alpha. Okay, so, and alpha is root 3 over 2. But I'm just going to highlight this because I still have to demonstrate that the integral here is log sec plus tan, log sec plus tan. So that's a kind of a workings that I skipped over just because I'm running out of space. Actually, I could do it. I can do it on the side here. So if you have y equals log sec x plus tan x, then the derivative dy dx is 1 over sec x plus tan x times the derivative here. So I'll get back to this in a moment, but let me just check. Well, I'm in the middle of doing it. Okay, let me just check. Sec, what's the derivative of sec? Sec is 1 over cos. We did this a moment ago, didn't we? Bring down the power, reduce the power by 1, multiply by the inside. So it's tan sec, tan sine, plus, and then tan x is sec squared. So let's try and simplify this actually. That's sine. Did I do that one right? It's a sine tan or sine sec? Sine sec, isn't it? Sine sec, yeah. So that's sine over cos squared plus 1 over cos squared over 1 over cos plus sine over cos. If I multiply by cos squared, I'll get sine plus 1 over cos plus sine cos. Is that right? Oh yeah, and then I can take out the cos on the bottom and you're just left with 1 over cos, which is sec. So that means then, therefore, if the derivative of this is sec, it means the integration of sec is log sec x plus tan x. All right, now it's ready. Now it's time to sub in. I really hope this is right. A half times that times root 1 plus squared plus a half times log root 1 plus that squared plus that. So that would be 1.4841 minus 0 plus, then we'll put in 2 root 4 minus that squared plus 2, a half times 2 times root 2 plus 2 sine inverse that over 2. It's plus pi, makes sense, minus 2.2863664. $2.340. Man, I would be so happy if that's right. So happy. 0.852. Zero point eight. Okay. There a possible sign mistake? That would be really great. 1.4841 minus pi plus 2.2864. No. Oh, well, I did say actually that was only for area A, and I wasn't sure which area we were dealing with at the back. I do remember that. So what I just calculated was this area. So I don't think, or if I'm going to be right, and it's possibly the white areas, then it would be 2 pi minus twice my answer. No, not either. Not that either. So that's okay. Hang on. Okay, let's check now if this one is right. Square root 4 minus x squared alpha to 2. Zero 0.85. Yeah, okay, good. Right, so that's good to know that that's right. So it must be a problem with the other one. Surprising. Hmm. Oh, well, I typed that in backwards, so it's 1.4. Oh, that's what I got. Interesting. So believe it or not, my answers are correct here. So the A is 2.30. Okay, so that's 2.34. That's 2.34. That's 0.801, and that's 0.801. The answer at the back, 0.852. Let's check it now. So let's solve these two. So 4 minus y squared x equals, and then y squared equals 1 plus x squared. So I can definitely say that's square root. Take a positive one only. Oh, Did I make a mistake? Oh yeah, I left out the root here. Let's try it again. X equals square root 4 minus y squared. Yeah, so yeah, it's definitely square root 4 minus x squared. Okay, and then the other one is root 1 plus x squared. Okay. Okay. And then solve. Maybe I just found the wrong intersection point out. Oh, root 6 over 2. Must have made a mistake earlier. So root 6 over 2 for alpha. So maybe, just maybe, fixes it up. Okay. I can't believe solving these two were the part I made the mistake of. Ridiculous. Okay, root 6 divided by 2. Okay. Oh, actually, I don't need to delete all of it because it's only this one I need to change. I don't have it on the calculator. Okay, half that root 1 plus that squared plus a half log root 1 plus that squared plus that. So that is 1.4841. And then okay, then half that root that over 2. Huh? Why is it the same number? Oh, because root 3 over 2, same as root 6 over 2? Or just by coincidence, I get the same value. Oh, because, yeah, I can multiply above and below by root 2. So, yeah, okay, so actually, no, my value was right. So let's continue here. Okay, so what the area I got was this piece here, so that would be underneath the quadratic one, which is the root. So that's line 5 integrated. And then line 4 integrated. Then 11 plus 14, 2.33. Yeah, 2.339. I got 2.340. So if I was being a little bit more precise with my rounding, it'll be 2.34. Oh yeah, no, it rounds off the tree. Just replace the same. Okay, so why does the answer differ with the one at the back so much? 0.852. So I guess they probably, actually, now that I think about it, if it's the area bound between the two, they probably want this. So it'd be pi minus that answer. Which is 0.802. Yeah, so this area here then would be 0.802. But it's not clear which area they want. For the following exercise, find the exact area of the region bounded by the given equations, if possible. If you are unable to determine the intersection, I don't know. Maybe I'll open a ticket. I suppose here. Yeah. It's actually isn't any bound area when I think about it, unless you count the. Does it say with an axis? Yeah, there isn't actually. When I think about it now, there isn't any region bounded because. Well, yeah, because of the root here, the x has to be positive, so it has to be to the right. Hmm. Hmm. Actually, yeah, I should definitely open a ticket. Ooh, tough question, but I think I would say 0.802, and that's if you add in the positive y-axis. Okay, okay. Actually didn't make, I don't think I made a mistake here, even when I thought I made a mistake with the root 3/2. That actually is the same thing as root 6/2. Root 3/2, that's what I had originally. That's the same thing. So, yeah,